Let's quickly go over the derivation of the second form of the magnetic force law, which is the form that can be written as F is equal to I L vector cross B vector. All right. So let's start by considering the effect of a uniform field acting on a length L of wire that carries a current of I. The current in the wire is going to consist of moving charged particles, and so each of those charged particles will experience a force due to the magnetic field that it's in. Recall from chapter 27 that we have an equation that gives the conventional current running through a wire in terms of this cross-sectional area of the wire, the charge magnitude of the charge carriers, the number density of charge carriers in the wire, and a thing called the drift velocity, which is a measure of the net average velocity of the charge carriers flowing through the wire. Our goal here is to rewrite the magnetic force law, force is equal to QV cross B, in terms of conventional current running through a wire instead of individual charges. We see here that we have our original equation for the magnetic force law is in terms of velocity of individual charges. So it makes sense that we can maybe substitute in the drift velocity, which represents the average velocity of the charges in the wire. So what we're going to do is we're going to take this equation and we're going to rewrite it so that we have the drift velocity in terms of the conventional current, the number density of charges, the magnitude of the charge on the charge carriers, and the cross-sectional area of the wire. We will then take this drift velocity expression and substitute it into the original magnetic force law. But notice that what we've written over here is the magnitude of the drift velocity, and over here we need a velocity vector. Right? But we know that the drift velocity is in the direction of the current running this way in the diagram. So what we'll do is we'll define a vector L that points in the same direction as the current, and we'll define that direction with the unit vector L hat. And the magnitude of that vector is just a particular length of wire that we're interested in. All right, so what we can do here is we can now turn this into a vector by giving it a direction in the direction of the conventional current, which we're going to call L hat. So now we can legitimately substitute this drift velocity vector in for this particle velocity vector. And that gives us the force, and we'll be very specific here. This is the force on a single charge is equal to Q drift velocity cross B. But that gives us Q times I over NQA in the direction of this L hat unit vector, and that is crossed with B vector. Notice that the charges here will cancel, leaving us with I over NA times L hat cross B vector. Now remember what N stood for. N was the number of charges per unit volume. This is the number density of charges in the wire. So that means N is the number of charges per volume, which we can write as being equal to big N, which we'll use this to represent the total number of charges, divided by the volume, which we'll write out. But volume for this wire, for a cylindrical wire, is the area of the cross-sectional area of the wire times the length of the wire. So now, if we want the force on the entire wire, what we're going to do is we're going to multiply the number of charges in the wire, in that segment of wire, times the force due to a single charge, right? Because if we have the force due to a single charge, we multiply by the number of charges that are having this force applied to it, we'll get the total force on the wire. But that gives us N times this whole thing right here for the force on a single charge, which is I over NA L hat cross B vector. But N, we just decided back here that N is equivalent to capital N over area times distance. So that lets us write this as big N here, I. The little n will replace with big N over AL. Gets flipped over because it's on the bottom. And we still have this A to contend with, so we bring that A down here. And that gives us left with a L hat times B vector. And now we see a bunch of stuff cancels. This N cancels with this big N. The area cancels here. And we are left with the force on the wire being equal to I L times L hat cross B vector. But the magnitude of L times L hat is just L vector. So finally, that gives us the final equation we were hoping to derive, which is something you should know, and that is the force on a wire is equal to IL cross B.